So I'm going to talk about multiparameter tests of general relativity using compact binary coalescences. And this talk will be based on a few papers that was written in collaboration with Anuradha, Shilpa, Saurabh, Salim, Arun and Satya. So this test primarily focuses on the in spiral part of the gravitational wave signal. Um, uh, so, uh, so that is where we will focus on. So this is a schematic diagram of the curvature potential phase space that is sampled by various tests of GR. As you go to the right and climb up the y-axis, your curvature and potential becomes increasingly large and dynamical, and that is exactly what is spanned by the first two gravitational wave detections, GW 15 12 26 and GW 15 1 14. So these really provide us with a unique opportunity to test GR in this kind of energy scales. Um, uh, uh, so um, you have seen this diagram a lot of times, which shows the evolution of compact binary through time, and this is a typical signal that you get from it. And like I said earlier, we are going to focus on the in spiral, where the compact binaries are slowly orbiting each other. So at that phase, you can perturbatively expand both the amplitude and phase of the gravitational waveform in terms of V by C, which is shown in equation 2. And this phi k and phi kls that you see are called these post-Newtonian coefficients, and this are in GR. These are all uniquely determined by the mass and spins and other intrinsic parameters of the binary. And these are really rich in structure. By that I mean that they encapsulate a lot of non-linear effects as well as physical effects and so on. For example, from 1.5 pn, which is the correction at v to the power 3, you have both gravitational wave tails as well as spin orbit interactions coming in. So there's a lot of physics going on. In the most theory agnostic manner, you would expect this multiple pn coefficients to get altered if the interactions between the components are like different in some alternate theory of gravity. So our goal would be to measure the different PN coefficients and test how consistent they are with GR. So for this, we follow this null parameterization, where we add this extra deviation parameter delta phi on top of the PN coefficients in GR. So, and in GR they will take the value of 0, and it can have a non-zero value in any alternate theory of gravity. And these are the free parameters which we will try to constrain. Yeah. So now that we have gone through a bit on parameterized tests, so there could be two classes depend on how many parameters you are keeping free. And I mean, in the most general way, you would like to simultaneously test all these parameters, because like I said earlier, there could be like there's it's only natural to expect that deformations may occur in multiple PN orders depending on the physical interaction involved. In that case, your parameter space will have all the GR parameters, which are like mass, spins, inclination, angle, so on, and a multiple number of deformation parameters, which can vary from 2 to 8 depending on like which is what is accommodated by a phasing correct up to 3.5 PN order. But this turned out to be really difficult because the PN coefficients are highly correlated among each other, as well as like with the intrinsic parameters of the system. So what people do is they resort to this single parameter test where they they vary one of the deformation parameters and keep the rest of them fixed to the GR value. So this is a rather restricted approach, but turns out to be useful under certain assumptions, and is what is routinely followed by LVK. But this is like a example of how the multiparameter test fails when you try to do them with the present detector sensitivities we have. So this is like the posteriors on all these deformation parameters from the real event signal of GW 15, 12, 26. So a good posterior would peak at 0. I mean, if the GR is correct. However, as you can see, these posteriors are all over the place. So yeah. So how do we overcome this problem associated with this multi-parameter test? We could actually take two roads. Given our present detector sensitivities with advanced LIGO and Virgo, we can use the method of principal component analysis, where you basically transform to to a different space where your bases are uncorrelated, or this new parameters are uncorrelated among each other. And the second approach would be to use future gravitational wave third generation gravitational wave detectors like Cosmic Explorer, Einstein Telescope, and LISA, and make use of their better sensitivities as well as information from both like space-based and ground-based detectors, and combine them coherently. And we will see later that it actually helps to lift this degeneracies and actually perform the test. So first we'll quickly discuss the PCA aspect of multiparameter test, and these are again the posteriors on GW 15, 12, 26, but now on the PCA parameters. And you can see like the first two PCA parameters are very well constrained and is very well consistent with 0. And you can see from equation 2 that these PCA parameters are linear combinations of the original parameters. So any measurement on them is like a simultaneous measurement on all the original parameters. um, and it turns out that if you consider the first two leading order PCA parameters, they encapsulate almost all the information you have. um, and we do this on all the on these five gravitational wave events which we detected during the first and um, second observing time. And we found that the leading PCA parameter performs really well, and is very well consistent with GR prediction. um, and now let's move over to the multiband aspect and how we can use this to do this multi-parameter tests. Um, so this plot shows the sensitivity curves of the various detectors, which are plotted in dashed lines, and the solid lines show the characteristic amplitude of GW 150914 and a system of 500 solar mass. And this sudden drop shows like the depicts the merger of these systems. So as you can see, like 5 years prior to their merger, this the amplitudes fall well within the millihertz band of LISA, and as they evolve, uh, the late time dynamics close to the merger and ring down is visible in the ground based detector bandwidth, which is the kilohertz regime. So we can actually use this double observation and gather the information from both the bands and coherently combine them and see if it helps our purpose. um, and it turns out that yes, it does. So this is this is a plot on the 1 pn deformation parameter on the left and 3.5 on the right. So the black arrow, it shows the difference in the bounds when you use only one of the detectors, lisa, ce, or et, and when you combine do the multibanding and then find the bounds, we see there's like an order of magnitude improvement, mm, um, which 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 we find and can be traced back to the fact that these correlations are lifted because they are really of opposite nature at both the frequency bands. They are rather complementary. So if for example, if delta phi to chirp mass correlation is positive in lisa, it turns out to be negative in c. So when you add them, they really cancel, and there is a large scale cancellation of this way between various parameters, which really gives this improvement factor. These are, by the way, from one parameter test. So now, since we have this know about this improvement, we try to assess this from multi-parameter point of view. So for that, we make a population of 10 to the power 5 stellar mass binary black holes, following the masses and redshift distributions that is given by the first gravitational wave transient catalog. And we find
Anthony, you
out.
have 5 minutes. Okay.
Yeah, sure. Thank you. Yeah, so out of this 10 to the power 5 stellar mass parallel black holes, we find that only 200 of them are visible both by LISA and CE. So these 200 binary black holes are our multiband candidates, which we will use for this test. And this is the plot that shows the measurements from various multi-parameter tests, and it go this black dots are from one parameter test, and as you keep adding more and more of this deformation parameters going to higher multi-parameter test, your bounds worsen for obvious reason that you're increasing more parameters in your system. But yet the marks shown by these hollow octagons, they give the bounds from the 8 parameter test, and it looks like and it shows that all the post Newtonian deformation parameters can be tested simultaneously with the GR parameters to less than 10% accuracy. And I mean, even if you had taken like golden binaries, the systems that are best sensitive to lisa and ce, and tried to perform multi-parameter test with them separately, their bounds wouldn't be these bounds are much worse. So these are denoted by this orange and purple marks. So they are still much worse than what you get from the 8 parameter test yeah, after doing multibanding. So this is probably could be the only way to do this multi-parameter test in the future. um, yeah so I think I'll so in the conclusion, to conclude, I showed that we can perform this multi-parameter tests of GR, which with the help of PCA, which will allow us to test like the overall PN structure of the theory. And we can and we can also perform this using multiband observations, and and it turns out that it facilitates 8 parameter test up to less than 10% accuracy, whereas the lower PN coefficients are constrained to less than 0.01 accuracy. Yeah, I think that's all I had to say. Thank you, and I'll take any questions if there are.